Imagine taking a walk, but instead of pavement, the world is coated in perfectly smooth ice. When you step forward, your foot slides straight back. That sliding happens because you are missing friction. Friction is the invisible, resistive pushback that happens anytime two surfaces rub against each other. We usually notice it when it causes a problem, like wearing down the soles of your favorite shoes or making an engine overheat. But without that resistance, you couldn't drive a car. You couldn't even hold your phone. It would just slip right out of your hand. This resistance holds structures together. When you tie a knot, it stays secure because the rough fibers of the rope physically grip onto one another. Friction provides the essential grip that makes all movement and stability possible in our physical world. To understand how this grip actually works, we have to look much closer. If you run your hand over a wooden table, it might feel completely smooth. Zooming in to a microscopic level, that smoothness disappears. Every solid surface features tiny, jagged edges, like miniature mountain ranges. When you slide one object over another, these microscopic mountains crash and snag into each other. That snagging creates the resistive force. You have felt this directly if you've ever tried to push a heavy piece of furniture, like a bookcase, across a room. It takes a lot of effort to get that bookcase moving. The physical exhaustion you feel is the macroscopic result of forcing millions of those microscopic mountains to break apart and slide over each other. Getting that object moving happens in stages. When you first push and nothing moves, you're fighting static friction. As you push harder, you eventually reach the absolute ceiling of the floor's grip. This tipping point, right before the bookcase finally budges, is the limiting friction. Once the object is actually sliding, the resistance drops into a dynamic state. This moving friction is slightly weaker than that initial peak, which is why it takes less effort to keep the bookcase going than it did to start it. This chart shows the required force climbing, hitting a sharp peak at the limiting phase, then dropping once in motion. Turning the bookcase on its side to widen the contact area doesn't increase resistance. The graph stays identical. Both shapes require the exact same force. That is because total surface area doesn't change the physics of the grip. Friction really only depends on the types of materials involved and the downward weight pressing them into each other. Because the weight of the bookcase is what forces those microscopic mountains to lock together, spreading that weight over a larger area doesn't change the total resistance. If surface area doesn't increase grip, you might wonder why high-performance cars use such wide tires. Nose tires are wide to distribute heat and weight so the soft rubber doesn't melt, but the friction math stays the same. The real challenge comes when the road gets wet. When it rains, water pools on the asphalt. If a smooth tire hits that puddle, the water acts as a liquid barrier. The rubber glides right over the top, losing all contact with the road. This is why tires have grooves. As the tire presses down, it squeezes the water up into those empty channels, clearing it out of the way so the rubber can maintain its macroscopic grip on the pavement. While tires are designed to maximize grip, engineers often want to minimize it in other places to prevent energy loss and unwanted heat. These ball bearings are a great example. Instead of letting two flat metal parts slide against each other, they place small, perfectly round metal spheres between them. This allows the parts to roll, which dramatically reduces the contact points and lets everything move freely. We cannot bypass the laws of physics, but by understanding how materials interact, we can manipulate our environment to either grip tight or spin free based on what we need. You don't have to be an engineer to rely on this balance every single day. Every time you walk down a rainy sidewalk, hold a tool, or sit in a chair, you are participating in millions of tiny microscopic collisions. That invisible, dependable grip beneath your feet is the force that keeps your entire world intact.